Good afternoon, fans online. As many of you watching in various places, either the secondary school students, those who are preparing for the WAEC or the JAM, or those already in the higher institution who have passion for chemistry. In the last class, 2 days ago, I looked at organic chemistry, and yesterday we looked at calculus. That's the limit of function, and I'm sure quite a good number of you must have seen the video, and you must have also listened and probably learned one or two things. Today, very quickly, I will just be spending a few minutes to talk on the topic above. That's chemical bonding. Chemical bonding actually talked about the interactive forces binding molecules together. Okay, the interactive forces. So it's basically divided into what we call interatomic or intramolecular bonding or intermolecular bonding. Okay, so this is the basic way of categorizing chemical bonding. Interatomic bonding. Interatomic also can be called intramolecular bonding, and then you have intermolecular. Please, intra is different from inter. Okay, now the next thing is the inter or the intra is talking about the molecule within, while this is talking about different molecule. Okay, like in physics you have what we call adhesion and cohesion. Okay, now under this we have the following. We have the ionic bonding, we have the covalent bonding, we have the dative bonding. Ionic is also known as electrovalent bonding. Okay, dative bonding is also known as coordinate or coordinate covalent, okay, bonding. And then we have what we call metallic, okay, bonding. And here under our interatomic bonding, we have what we call the hydrogen bonding and van der Waals forces. Van der Waals forces is further divided into two. We have what we call the London dispersion. The London dispersion is also known as your temporal dipole. Temporal, example, ethane, C2H6, which you can divide into CH3. That's your classic example of London dispersion. Okay, London dispersion is just telling you that molecule that are symmetrical, the same symmetrical molecule like ethane. Okay, then we have induced dipole. Okay, this is another example. Example of induced dipole is your polar covalent, like your HCl. Okay, now at the elementary level, you have been taught ionic bonding. That is the transfer of electron from a metallic atom to a non-metallic atom. That's very simple, and I'm not going to spend time on that. So you have example magnesium chloride, you have example calcium oxide, you have example calcium chloride, and so on. Okay, that's very simple. You transfer electron from metallic ion, for example sodium transferring one electron to calcium or to chlorine and all that. So but for the characteristics, you have also been taught about the characteristics of ionic bonding. For example, number one, We know that they are aggregate of ions and not molecule. Number 2, they tend to have high conductivity, high boiling point and melting point. 3, they are in aqueous, they are dissolved in water. That is, they are soluble in water. That's the ionic bonding. Not only that, the energy needed to break the bond of the ionic is very high. So we know that about the ionic. Then coming to the covalent, it's just the opposite of ionic. Covalent bonding basically talked about the sharing of the electron between the two participating atoms. For example, the formation of chlorine molecule, for example, the formation of carbon dioxide, okay, all of this, the formation of nitrogen molecule, chlorine molecule are all covalent bonding. So there's a sharing, okay. For example, you have hydrogen, you have this chlorine. For hydrogen, it is like monocovalent bonding. So you have this, and then for chlorine, it is monocovalent. For oxygen, it is dicovalent bonding. For nitrogen, it is tricovalent bonding. So you must know that. So characteristic of covalent bonding is, number 1, they are aggregate of molecules. Number 2, they have low melting point and boiling point. 3, they are insoluble in water, but they are soluble in organic solvents such as your ether, kerosene, benzene, and so on. Of course, the energy needed to break the bond is low in covalent. Okay, so they are usually non-polar. They are mainly non-polar. Okay, now the class quickly is talking about your dative bonding, which is also known as coordinate covalent bonding. And this is where a lot of students have problem. Coordinate covalent bonding. They do not understand what coordinate covalent bonding is all about. But I'd like to tell you that coordinate covalent bonding is a special kind of covalent bonding. It is used in the formation of hydrozonium ion, that is this, and ammonium ion. This is called ammonium ion, and this is called hydrozonium ion. So it is used in this formation, ammonium ions and hydrozonium ion. Okay. Coordinate covalent bonding is used in the formation of ligands, or complexes. Okay, now let's practicalize it quickly. Now you have this, for example, and then to form this, which is this. Now you have this, and then to form this. Okay, quickly, so you can see what we are talking about now. This is ammonia and this is hydrogen in the formation of hydrozonium ion. Now what really happened? What is the issue? Now students know, okay, who donates the electron. In this formation, it should be noted that it is a central atom. The central atom here is known as your ammonia. The central atom is known as ammonia. For the campus student, you want to know, how do you find your central atom? The central atom is known by the one that is least electronegative or less electronegative. Here, except hydrogen. Please, there's an exception here so that you don't quote me elsewhere that I said this. There's an exception. The exception is hydrogen. So where you have, for example, boron trifluoride, you want to know which is the central atom. Obviously, it's going to be boron. Why? Boron is less electronegative compared to fluorine. But here now, this is the central atom. So now, how many lone pair are there in ammonia? Students know that it is one lone pair. But you ask them, how do they know it is one lone pair? They don't know, they only can. You ask a student, how many lone pair do you have in water? They can easily tell you that lone pair in water is just 2. You ask, how do you know it's 2? You say, I saw it in textbook. They don't know, they cannot solve, they cannot explain further. You ask them, is there lone pair in boron trifluoride? Is there lone pair in phosphorus trichloride? Is there lone pair in phosphorus pentachloride? They don't know, because they only did they only saw what they saw in textbook, and they cannot really explain. So but let's quickly do something as I'll be rounding up the class. Okay, as I'll be rounding up the class. So now in determining lone pair in this coordinate covalent bonding, which is a special covalent bonding, in covalent coordinate covalent bonding, only one atom donates the electron. Remember, in the ordinary covalent, the 2 contributes the atom, but here only one donates the electron that is used in the bonding, and you must know that only one, and that makes it very special. And how do you determine lone pair in the bonding? Please quickly let me tell our campus people who are listening this, that total electron pair is equals to lone pair plus bond pair. Total electron pair is equals to lone pair plus bond pair. Total electron pair, and it should be noted that lone pair are greater than lone pair bond pair, and lone pair bond pair are greater than bond pair bond pair. Please, our students on the campus must note this carefully. Now, what do we mean? In ammonia, how do I know it is one lone pair? Please, time will not permit me to go in detail. The central atom has been determined as nitrogen. How many atoms are around nitrogen? Let's find out. The first question, what's the valence electron here in nitrogen? 5. How do I know it's 5? Look at it. 2. Nitrogen is 7. 2, 5. So the valence electron is 5. Okay, so that's 2, 5. So you have 5, and then hydrogen is 1 times 3, so you have 8. So the total available electron around ammonia is 8. Now the question is, how many are used during the bonding? Let's check up. Only 6. How do I know? Each of these represents 2 electrons, so you have 6. This one that is not being used during the bonding is what we refer to as lone pair. That's what we refer as lone pair. And lone pair are stronger. What do? They alter the shape of the molecule, so they are stronger than the bond pair. So we have total electron pair to be 8. Only 6 are used, 2, 2, 2. And this 2 that is not used is referred to as the lone pair. I show you water as I close this chapter very quickly. Look at water, for example. The total, what's the central atom here? Oxygen. The total electron here is 6. Oxygen is 8, 2, 6. So you have 8. So you have 8 electrons. Okay, now, so let's now draw oxygen. Drawing oxygen, you have this. Good. And then only 4 are used. 4 bond pair, and the 4 that are not used here are called the lone pair. That's why we said that there are 2 lone pair in oxygen. Do you understand now? So now somebody may now want to ask, is there lone pair in methane? There is no lone pair in methane. Why? Because everything is used. Look at methane. Carbon is 8, carbon is 6, rather 2, 4. So you have 4 electrons, and then you have 4 electrons, 8 electrons. So look at carbon. Look at methane. Everything is used. 2 times 4. So this one will not have lone pair because everything is used during the bond. That's how to identify. So in my next class, I am going to be explaining to you the Van der Waals forces, and then explaining what we mean by London dispersion. I told you it's temporal dipole, and then induced dipole interaction. What is significant? Please let me close with hydrogen bonding. Hydrogen bonding is the bond between hydrogen and small but highly electronegative elements such as fluorine, oxygen, and nitrogen. The bond between hydrogen and these three elements. Basically, in a book of Philip Matthew, I think you are likely to see chlorine in one advanced chemistry book of Philip Matthew. Okay, but basically at the elementary level, you should take these three. Okay, so it means that water has hydrogen bonding, ammonia has hydrogen bonding, hydrogen fluoride has hydrogen bonding. Okay, please take note of that. Now, what's the significance of hydrogen bonding? Any compound that possesses hydrogen bonds are likely to have relatively high boiling point. That is significant of hydrogen bonding. You must note that. As we close the class, it should be noted that the factors, that is, it should be noted that hydrogen bonding in this is higher than this is for those on campus. Hydrogen bonding in ethanoic acid is higher than that of ethanol. Why? Because here there are two dimers being formed, dimerization. Here only one dimer. Number two, here the boiling point here is higher, about 60. The boiling point is higher, okay, and then the boiling point here is higher than there. Not only that, the molecular mass, okay, let's use molecular mass. The molecular mass of this one is higher than this. So that's telling you something, that the factors is not just the hydrogen bonding. The fact that this one formed two dimers at a time. Dimerization is an opposite of dissociation. And the fact that the boiling point of this, or the molecular weight of this, is higher than this. So take note of all of this in bonding. Till I come next time, do have an amazing day. God bless you all.